One scientist said that if conditions were right, life could originate anywhere in the universe. Arrhenius, a Swedish chemist who died in 1927, expounded this theory of panspermia. He believed that life is universally diffused. Life, he felt, was constantly emitted from all habitable worlds in the form of spores, which traverse space for years or ages, the majority being ultimately destroyed by the heat of some blazing star, but some few finding a resting place on bodies which have reached the habitable stage. Life Elsewhere is our program today. In the following moments, we will see where and how man is looking for life outside of Earth. Let's begin by viewing a brief segment on the famous Halley's Comet and see a program that NASA considered but dropped and that would have intercepted the comet in 1986.
Halley's Comet began its first journey around the Sun thousands of years ago. It will come near Earth again in 1986, and NASA and the Jet Propulsion Laboratory are studying a mission to intercept it with a spacecraft. It is an opportunity unique in our lifetime to investigate the best-known comet of all at close range. The proposed Halley spacecraft would use hardware and technology from the successful Voyager mission to Jupiter and Saturn, and from the developing Galileo mission to orbit Jupiter. It would be equipped to examine the comet in detail. It will carry a new electronic camera to produce highly detailed color pictures. Other instruments, many from Voyager, to reveal its chemistry, record its ultraviolet and infrared radiation, measure its magnetic field, and collect samples of its dust. This unique mission would begin in summer 1985. NASA's new space shuttle will launch the American probe on its 8-month journey to Halley. Similar missions are already being planned by European, Japanese, and Soviet space teams. Guiding the spacecraft to a successful encounter requires the kinds of pinpoint navigation techniques we have learned in 20 years of space exploration. Intercept would occur after Halley passes the Sun. A full 2 months before encounter, cameras aboard the spacecraft will begin taking pictures, returning thousands of photographs to Earth. Probing within 500 miles of the nucleus, our robot will give us our first look at the heart of Halley's great comet and a glimpse back to the dramatic moments of the birth of the solar system.
Meteorites have scarred the moon's surface for millions of years. Many of the moon's craters were a result of meteoric impact. Occasionally, these visitors from space fall to Earth. They have been found to contain amino acids. As we learned in our last program, amino acids are the elementary building blocks of life. For the next few minutes, we will see some investigations done on meteorites found in Antarctica.
These visitors from outer space come in a variety of shapes, sizes, and colors. They are meteorites, some 4.5 billion years old. And they are being found in relatively large numbers in Antarctica. 1,300 have been collected during the last few years. The total number of meteorites in collections around the world was only 2,000 before the Antarctica finds. So the discoveries there have come as a tremendous surprise to scientists interested in doing research on these cosmic travelers. The meteorites are really small fragments from an asteroid belt that might have helped form a planet. Many of them are drawn into the orbits of Jupiter, Mars, or even the Earth. So here in Antarctica, preserved by its icy conditions, is some of the oldest material of the solar system. Some of the very material that went to make up Earth, for example. By studying meteorites, scientists hope to find answers to two very fundamental questions. Is there life beyond Earth? And what are the processes that led to life on Earth? NASA and the National Science Foundation have been working together to preserve the meteorites for careful analysis. At the Johnson Space Center's Lunar Receiving Laboratory, the meteorites are prepared for distribution to scientists all over the world. They are handled similar to the way samples returned from the moon by the astronauts are handled. One of the people analyzing the meteorites is Dr. Cyril Ponemparuma, director of the University of Maryland's Laboratory of Chemical Evolution.
See, what we are trying to find out in the meteorites is to see whether there are any of these molecules related to life. There are certain molecules like the amino acids which may be described as the building blocks of life. The meteorites present to us the only prebiotic matter we have laid hands on. So we like to find out whether in this meteorite, in these samples, are any amino acids, any hydrocarbons. So the process is one of extracting the meteorite, taking the molecules that are in there, dissolving them in a solvent that will get them out. Then we have a small amount of liquid that will contain some of these molecules. At that point, we will go to a gas chromatograph, an instrument that will separate this component. We will inject a very tiny sample into a gas chromatograph and see whether these individual components can be picked up by a detector.
Dr. Ponemparuma has found organic compounds in the meteorites, organic compounds which are necessary for all life, and they are different from any found in living organisms on Earth.
What does that imply is that all those events that led to life may be common in the universe. So what we said happened on the Earth may be happening somewhere else.
This is a piece of the Murchison meteorite, which fell over Australia in 1969. It's of a rare type called carbonaceous chondrites. AIM scientists are analyzing meteorites such as these to learn what light they may shed on the history of chemical evolution elsewhere in the universe. The outer portions may be contaminated by Earth life, so they are first sliced away. Then the core is sectioned, pulverized, and chemically treated to remove all organic or carbon compounds. The organics are further separated into classes of compounds, such as amino acids and hydrocarbons. To learn exactly which compounds are present in the meteorite and whether they're sorted by handedness, we may use this powerful analytic system, a gas chromatograph coupled with a mass spectrometer. The organics are injected into a stream of helium flowing through a long coil of very fine tubing. It's 150 feet long and only 2/100ths of an inch in diameter. An inner coating on the tubing causes the different compounds to migrate along at slightly different speeds. Thus, when the sample emerges from the gas chromatograph coil, the different molecules are clustered in bunches like bicycle racers. A detector reports how much of each compound is present. Double peaks like this indicate the presence of both right and left-handed molecules. For a precise analysis of the atomic makeup of each compound, the output of the coil may be fed into a mass spectrometer. Here, each compound in turn is ionized or broken into fragments possessing detectable charges. Then the instrument literally counts the number of atoms of each atomic mass and charts the results. Finally, by computer processing, it's possible to reconstruct the compound and usually give it its precise name. With techniques like these, NASA scientists have found that the Murchison meteorite has an amino acid distribution similar to the residue created in the laboratory flask spark discharge experiment, and a carbon isotopic composition similar to the pre-life African rock sample we saw. Thus, this meteorite study supports the theory that chemical evolution has, in fact, produced the building blocks of life throughout the universe, thereby paving the way for biology to come on the scene.
Now let's take a look at what scientists in the early 60s felt that they would find on other planets. We will see some sterilization techniques used in spacecraft. It is very important to send a sterilized spacecraft to land on another planet. We do not want to contaminate the other planets with microorganisms from Earth.
Dr. Fox, what kind of chemistry do you expect to find in living cells on other planets? I would expect to find nucleic acids, and I would expect to find protein similar to the protein that we have on the Earth and similar to what we have been able to produce like protein in the laboratory under conditions that might apply on other planets.
Would other life have to be that much like our own chemically?
Well, it is possible to imagine that systems in which other kinds of polymers replaced proteins and nucleic acids. Basically, our problem is one of finding out what is the possible latitude for the chemical constitution of protoplasm.
Dr. Letterberg, could you outline your reasons for studying life beyond the Earth?
The outstanding one is that exobiology affords us a fresh, new approach to the fundamental questions of the origins and diversity of life on a cosmic scale.
I understand you have some concrete plans for the study of life on Mars.
Well, there are many possible approaches, but we might build one of them around the landing of a microscope on the planet. This would be an instrument essentially comparable to the bench model that we have here, although of course it would have to be considerably reduced in size and assembled for automatic operation.
Why a microscope?
Well, for many reasons, microscopic organisms are good prospects in the search for extraterrestrial life. We should expect such small organisms to flourish best under minimal environmental conditions. In addition, microbes should have evolved before larger organisms have.
Then microbes are really the basic form of life.
In a sense, at least they are found universally, whereas it might be a matter of some chance whether a single random spot on the Earth's surface contained a larger plant or animal. We could expect to find traces of microscopic life in every drop of water, gust of wind, or a pinch of dust.
And the same thing might be true on Mars?
Yes, we would think that we would have our best chances of finding microbes on other planets as compared to other organisms. The introduction of microorganisms to a previously sterile or barren planet could result in the rapid spread of these organisms. One may calculate that given dissemination by winds and currents, organisms could occupy a volume the size of the Earth within a matter of days or weeks, limited only by the ultimate exhaustion of the nutrients in the medium.
What would be the consequences?
Well, among the consequences would be the obscuring of any previous life forms that might have existed, or a chemical alteration of the native surface of the planet. We should also stress that there may be other than scientific values. We do not know the ways in which we will ultimately wish to exploit the resources of the planets. We do not want to introduce any circumstances or organisms that are likely to upset these original conditions. It follows that we must rigorously exclude terrestrial contaminants from our spacecraft. The group under Dr. Charles Phillips' leadership at the biological laboratories at Fort Detrick are doing a splendid job to make this a reality.
We considered various sterilization techniques and how they could best be applied to space vehicles. For a number of reasons, chemical sterilization with ethylene oxide gas seems surest and most convenient. The gas can be used atop a launching platform as easily as it can on the ground. Heat and radiation are more difficult to apply in unusual locations. Moreover, they might damage certain components. With the gas, all that is required is a chamber be built around the spacecraft which will hold the gas long enough for sterilization to take place.
Suppose a component is sensitive to ethylene oxide.
In that case, it could be sterilized previously by another technique and then shielded during ethylene oxide treatment by building a gas-tight barrier around it. Anything encased in a metal or certain plastics would be so protected.
Dr. Letterberg, is it possible that the Earth was seeded with life by the entrance of meteorite material from another planet?
This is the well-known theory of panspermia. Our present scientific information would make this a very unlikely possibility, but it is not one that we're in a position to rule out completely until we've had closer investigation of the conditions on other planets.
What are the long-range plans for putting scientific instruments on other planets?
In making these plans, we must work very closely with the engineers and scientists who will be designing and launching the vehicles. In due course, we may expect to have the capability of retrieving samples from the planets and returning them to the Earth. There is no question but that we can conduct our analyses more completely and more conveniently in the terrestrial laboratory.
Scientists at NASA Ames Research Center in California set up a simulated Martian environment in their laboratory in the early 60s to see if life could originate there. Information gained from this Mars box would be useful in planning future spacecraft to detect life on Mars. Let's take a look at this device with Dr. Richard Young.
Now, I should start out by stating that you simply can't put a planet in a box. But what we have constructed here is a chamber in which we can simulate many of the physical conditions that we know exist on the surface of Mars, and particularly those that have biological significance. We have a heavily insulated box, inside of which we have a second chamber which is capable of withstanding the stresses of pressure and so forth. The lid here is made of quartz so that we can contain the atmosphere and keep the pressure constant, and also irradiate in the ultraviolet. The upper end of the chamber, you can see we have a bowl cap formed which simulates that that exists on the in polar latitudes on Mars.
You actually have ice. How do you make it so cold?
Well, this is controlled by the use of liquid nitrogen tanks outside the chamber. We cycle nitrogen through the chamber and control the temperature at this end at about minus 100 degrees, which is approximates that on Mars. The high temperature, the sun, if you will, is done by using an infrared lamp, bringing the temperatures at this end of the chamber to about 80 degrees during the daytime. At night, however, it goes down to extremely cold temperatures, perhaps as much as 80 or 90 degrees below zero.
So this is the equator, and up there is we have the North Pole. What are all these little aluminum houses or wires? And
well, the wires we have in here are actually thermocouples that give us a temperature readout throughout the chamber, so that we know what the temperature is as a function of latitude and as a function of depth in the soil. This temperature then is actually read out for us on a strip chart, giving us at any given time the temperature profile. Cold at this end, this is at the polar end of the chamber then, on up to something like 70 degrees Fahrenheit at this end. The scale is in centigrade.
Well, that sounds rather pleasant.
Yes, the only problem is that at night it's quite different. At night it gets very cold, and from the point of view of biology, it's a tremendously rigorous environment. Now, we've then taken this chamber, pulled a dry Martian atmosphere through it, assuming that moisture was present on the primitive planet, pulled moisture out as it would have been lost to space.
Because of less gravity there.
Well, a rarer atmosphere and less gravity, right. The moisture then is controlled by these factors. Our objective was to see whether a permafrost layer, whether ice, would be tied up below the surface of the planet, since the average temperatures are so much colder, about 50 degrees colder than the Earth. In order to do that, we started cycling through Martian day, night, and seasonal cycles, and we found that this, by the way, is a longitudinal section of the chamber. We simply cut it in half longitudinally. We find that the temperatures at the polar end are minus 100 degrees, at the equatorial end as high as plus 80 degrees, but perhaps as low as minus 90 degrees cycled daily. We found that a permafrost layer did form, and then a considerable amount of water was tied up below the surface of the planet. This permafrost layer was actually continuous with the pole cap that you can see in the chamber. Trace of water in the atmosphere, carbon dioxide and nitrogen, the primary components of the atmosphere. If this analogy is a good one, then all you need is a hotspot, if you will, a local hotspot on the surface of the planet, melting the permafrost layer, having water percolate to the surface, and you have the Martian equivalent of a hot spring or an oasis where biological activity may be quite abundant, let's say.
If there is life on Mars, how would we begin to search for it? Since manned spaceflight to Mars was, and still is, improbable in the near term, we sent probes to do our work. Now we are going to take a look at 3 early probes considered to be used to detect life on Mars.
This first device that we see here is called Gulliver. Its inventor is Dr. Gil Levin of Hazleton Laboratories in Virginia, and this is one of several devices that are being designed and prototypes are being built, ultimately to be landed on Mars to send information back concerning life, assuming there is life there. Now this one works very simply. What we have here is essentially a bullet which is fired out onto the surface of the planet, and you'll notice there's a string attached to the bullet. This is a sticky string that unreels onto the surface. The string is then reeled back into the chamber, into a chamber containing a nutrient medium. It could be sugar as the energy source. The string then, being sticky, will pick up whatever adheres to it on the surface, presumably dust or microorganisms or whatever happens to be there. If they find themselves in an environment in this chamber that's hospitable, in other words, if they can utilize glucose, they'll begin to grow. On the top of the chamber, we have a Geiger counter, a Geiger tube, a very simple, common Geiger tube. The glucose that's in there will be tagged isotopically. It'll be radioactive because we'll be using C14 in the glucose. If the organisms utilize glucose, they'll evolve then C14O2, carbon dioxide containing radioactive carbon. And all we have to do is count the radioactive carbon as it's evolved as a gas, as a waste product of biological activity. Now this chamber, or this device, is called the Wolf Trap. It was designed by Dr. Wolf Vishniak at the University of Rochester, and hence the name. It has a sampler as well, which is bounced out of the capsule itself onto the surface. These are both full-scale models, by the way.
I see.
This then will aspirate a sample by creating a vacuum, suck a sample of dust, if you will, into a chamber which might contain a growth medium very much like this one did. The difference here is that we're monitoring a different end product. In this case, we're looking for changes in pH. Assuming there are microorganisms, they will grow. They'll change the acidity or alkalinity of the medium. This can be measured by a pH electrode, which is in the chamber. So instead of looking for carbon dioxide evolution, we're looking for a change in the pH of the medium. Or also, in this, there's an optical device with which we can measure changes in the turbidity of the medium. If there are bacteria, for example, and they start to grow, they'll gradually cloud the medium so that the beam of light passing through will be attenuated. And this information also can be telemetered and give us, hopefully, direct evidence of biological activity. Much further down the line, when we have a capability of flying more sophisticated devices, perhaps in the later Voyager program, we would hope to land what amounts to an automated laboratory on the surface of a planet like Mars. It might look something like this, which was developed for us by the Aeroneutronic division of the Ford Motor Company.
Is this full size?
This is a quarter-scale model, so that the ultimate device might be more like the size of this table. This device it is a laboratory. It's a device that will do a multitude of analyses. It has soil probes, which can be used to loosen up the soil if it should be hard. It has a sample collecting system, which would actually take a core sample, or it might aspirate a sample the way that one does. It might have a sticky string array. The sample then could be brought back into the laboratory, stored for future analysis, treated chemically with an array of solvents, extracted. We have a gas chromatograph in here, a mass spectrometer, an array of spectrophotometric equipment. And it's a laboratory in a modest sense of the word, which we would hope to use on the surface of Mars to look for evidence of all of those basic attributes that we've been discussing: chemistry, metabolism, and growth. And it would take a fairly sophisticated device to do all of these things, needless to say. Of course, the fact that it is so sophisticated presents other problems, engineering problems primarily. The reliability of a device like this might be very difficult to compare to the reliability of a device like this. So we're really talking about a future generation of experimental device here.
Life from space. Was the Earth planted with the seeds of life in the past, as Arrhenius supposed? Do comets carry the materials of life about the solar system? We have more theory than evidence, and more studies need to be made. During this program, we learned that the building blocks of life, the amino acids, have been found on meteorites. We saw early scientific opinions towards the possibility of life elsewhere, and some devices that could be used to determine if life could exist on a planet like Mars. Next week, we will further explore the possibility of life on Mars Jupiter, and Venus, and see several simulated models and descriptions of the Martian surface. We will learn what our modern Viking lander sought and found on Mars, the planet, other than Earth, thought to have the best chance of life in our solar system. Join us then for our next program, Life on 3 Planets Beyond Earth. This is Lynn Bondurant saying goodbye from the NASA Lewis Research Center in Cleveland, Ohio.